So let me continue. He has a joint appointment between the Department of Physics and the College of Music. And as he writes himself, as both an artist and a scientist, my work is intrinsically inter and cross-disciplinary. My work in physics and in art is the natural extension of my practices as a creative thinker. At the core, I'm doing the same thing. The tools that I use to achieve the end goals are different, of course, but the conceptual framework is very similar. These two things talk to each other at a very deep level. So I hope you can convince us of that, and please, Marco, the floor is yours.
Thank you. Thank you, Anda. Thank you for the invitation. Thank you for being here. I mean, this is kind of a long, it's a kind of a long lecture, so feel free to interrupt me anytime. We will touch upon many different things, but I want to start with, sorry, this one not working. Oh, okay. I'll do it. I do like this.
You have to press the PowerPoint, that's okay. And then now it might work again.
I'll do it like this. Okay, the story here starts in 1977, and this is kind of the prologue for this lecture, when they launched the first Voyager mission with the idea of going to explore the frontiers of the solar system. And indeed, Voyager went all the way to the edges of the solar system, gave us impressive pictures of many different planets. But the thing here is that if you notice in this photograph, there are these two technicians that are mounting a disk on the outer shell of the spaceship. And this disk is this one, this gold disk, as you can see here, contains the sounds of the Earth. And if you look at the playlist, actually the diagram here is supposed to teach aliens how to actually listen to what is recorded here. And if you look at the playlist of this record, you see a lot of different, a lot of music. You have, from classical music, Bach, Mozart, I think there is some Beethoven somewhere, whatever. There are traditional music examples from many different parts of the world. There are sounds of the Earth. So there is this music corpus that has been sent out of the Earth into deeper space. And actually the Voyager is still going. It's still sending data back to Earth. So this disk is somewhere, I don't know, some minute or hour light from where we are now. Now the question is, suppose that at a certain point, this disk is actually acquired by a civilization that is very advanced, that has deep knowledge of math, physics, data, network, dynamical, complex system, but they don't know music at all. They completely lack the evolutionary structure that made music possible on Earth. So they know how to read the disk. They will figure it out. They know from the diagrams, they know from would they interpret this data. And so this is kind of the premise of this talk. Now, before we get into the deep down of which data we are talking about in music in general, I want to give you some sort of overview of thinking that we've been doing in the past few years now, almost 5 or 6 years, at the Santa Fe Institute, where I lead this initiative of music as a complex adaptive system. So our first meeting was in 2020, last meeting was last year. We dealt with many different aspects of complexity and music. from structural aspect to cognitive aspect. Last meeting was this past summer. We talked about evolution of music from a neurophysiological and cultural perspective and biological perspective. We talked about proto-music in animals and all these kind of fun things. So it's an ongoing project. I'm not an expert in all these areas of music complexity. I focus mostly on the structural aspect of music as a complex system. But for those of you who are interested in this approach, we produced an online course as part of this Complexity Explorer of the series of the San Rafael Institute. It is completely free, and this course is on music computation and complexity. The other thing that, you probably imagine from the nice introduction that Andre did, I'm very much into a computational mindset. So for me, computation is an integral part of both my science work and my music work. There is actually we also have a special issue of Advances in Complex Systems on music as a complex adaptive system. It's an open special issue, so we accept submissions at any time, and we are building this collection of papers that connect music with complexity in different ways. But what do we mean by music as a complex adaptive system? Well, music emerges at very different scales, both temporal, geographical, and societal. It's shaped by cognitive processes, interactions, environmental conditions, and physical limits of sounds. So sound is the medium, but sound can manifest itself in many different ways. So there is sound as we now can kind of interpret like the classical music concert. We go to a theater and listen to music, or we go to a pop concert and we dance, or we go and, we use music in rituals and coordination of collective action in a stadium, for instance, and so on. So it's, as you see, that you can look at music in a complex way, as a complex system at many different scales and many different environments. Music is continuously evolving, and it's an entity that emerges from the interaction of different elements. And so here is a little bit of this scaffold, if you want, because I'm very interested in these two first rung of the ladder, where we look at the emergence of pitch and sound from single tones or individual elemental sounds, the construction of how these elements are put together in a melodic or harmonic context, and then you can scale up and you look at the performance, you look at the evolution of genres and all these kind of things. But this is always in a kind of a feedback loop where things evolve, but they always kind of fed back into the system itself. One of the hypotheses or kind of the stepping stones of this work that we are doing to look at the music as a complex adaptive system is that we believe that products of music are examples of emergent complexity. And I'll show you some ideas in this context of how I see emergence, for instance, in music. Okay, so again, behaviorally and culturally, music operates on nested timescales. They are all interactive. So from a cognitive perspective, for a kind of experiential and growth of our own kind of cognitive tools. socio-cultural evolution, so music technologies evolve, they evolve music, and music feedbacks into the evolution of other technologies. So it's a whole ecosystem. I don't know that Andre doesn't like that I use the word ecosystem here, but I still use the word. And I was saying earlier, like the evolution of music seen from a biological and neurological perspective. So music perception. I already mentioned this many times, but here is where also it connects to the aspect of cultural evolution and how we form aesthetic norms and how we interpret music as different people, different cultures, and different geographical locations. But the bottom line is that, yes, this is a complex system. A complex system can be represented using a network that defines the interaction between the components. And so my point, kind of after this long introduction, I want to show you how I view the structure of music. And when I say structure of music, I refer mostly to the Western classical music tradition, can be actually seen as a network process, and how this realization teaches us something about the music itself. Okay, so data. I believe most of you know what a network is. Just as a refresher, a network is made by a collection of data points that are the nodes of the network, connected by links depending on the relationship that exists between these data points. So this is a classical example of a network of airports and flights between airports. It's a transportation, an example of a transportation network, but there are many different networks that one can construct, as probably most of you know, so I don't want to dwell on this for too long. What I want to tell you, though, is the two main quantitative measures that I use in my work in music to define these networks and what information I can gather from the analysis of this quantitative, this quantity. The quantities are the degree of the nodes and the community structure of the network. So I will be talking about nodes and looking at nodes as particular elements of music theory in a way. And the community structure is how these nodes are arranged together. And in particular, I will look at modularity measures and that give me information about the underlying topology of the network. So I don't need to, we don't need to talk about this. I mean, we will see that we can look at network of music both in a directed and undirected fashion, and what it means from one point of view or the other. Talking about modularity, this is an example that I like also always to put in my talks. This is my Facebook network that I downloaded at the very beginning of when Facebook allowed you to download this kind of data. Now they don't give it to you anymore. But speaking of modularity structure and community structure, you see that there are nodes that are clustered together, and these nodes actually give me, I know who is part of these nodes. So for instance, here I believe I have all my composers, musician friends. Here are my physicist friends. Here are my Italian friends. And you see how this cluster together and give me, they kind of make the topology of this network way richer. And I'm not here in this network. This person at the center is my wife, so she's the one that is connected to most of these nodes with me. Okay, so let's go back to this and talk about how music is data and is networks. Of course, you need a data set, and the data set can be as varied as, you know, a melody. I can look at melody as my primary space of data. I can look at harmony as my primary space of data, or rhythm, or orchestration, or timbre. I can build a data set using any of these different spaces. And as I said earlier, I will be moving today within the Western classical music tradition, but what I'm going to say applies to any music tradition all over the world, irrespective of, you know, temperaments and stuff like that. So the basic data point or components, say, of this data set are pitches. And in Western classical music, overwhelmingly we work with 12 different pitches in the temperate, equal temperate scale. As I said before, this constraint can be released, and you can work with as many pitches you want, so you have different scales and different temperaments you can define, but for now we work within this particular framework. And just incidentally, how many of you know music? Okay, the majority, so I think that if you have questions, just ask me. What I'm really interested in this work, though, is not just the pitch itself, but is the combination of pitches. So, in this famous short story by Jorge Luis Borges, The Library of Babel, the argument is that there exists a library in the universe that contains all the possible combination of all the possible 27 orthographic symbols, so that in this library you might have books that are all A's, books that are all B's, but also once every, I don't know, some order of trillions, you might have the Odyssey or the Iliad, because combinatorially eventually you can get one of these books in this universe. Now, of course, this is paradoxical, but the idea here is that in music we have 12 symbols, our pitches, but these symbols don't carry meaning as words carry meaning. So indeed we can construct combinatorially combination of all these pitches in objects that then are our chords. So if I play 2 pitches together, I have an interval. If I play 3 pitches together, I have a chord. And I can build chords using all the notes, say, of a piano keyboard, and see how many chords can I build. Well, the number that you can build is still enormous. Even if you reduce the degrees of freedom of your constraints, so that basically you don't want duplicate notes, you don't want, you don't consider ordering as essential in this classification, and you reduce this way the number of possible simultaneous notes that you play. If you use only 12 notes, you can build 4,096 independent sets. If you use 24 notes, you have 16, almost 17 millions, but if you use the whole keyboard, you have 10 to the 26 possibilities, so basically the number of particles in 1 centimeter cube of material. So it's a huge space. We reduce it in various ways, so we can kind of.
Marco?
Yes.
A set is 2 or more notes?
2 or more notes. Well, actually, 1 is also part of this.
Yeah, okay, but you don't put a maximum.
The maximum is 12.
12. Okay.
Yeah.
Not 88?
Well, no. In this one is 88.
Yeah,
sorry. In this one is 88. Yeah. This one is 12. This is 24. So, this one reduces if you say I want to have only, say, 12 nodes over 88. Then it becomes the binomial factor of 12 over 88. Okay, so I want to build a geometrical model of this harmonic space. And in order to do this, I need to define chords. And I define chords as vectors, so that numerically they can be represented as vectors, as collections, lists of numbers from 0 to 11. This is one of the interesting aspects of working with this kind of spaces. This numerical space is the modulo 12 space, and as consequences the way in which many of these topological things emerge. And in order to have a geometrical model, I need to have points, but I also need to have distances. And so I define distance using a Euclidean metric that allows me to say how far what two chords are from each other. Now, you might object that in this space I have chords of 3 nodes and chords of 4 nodes and chords of 5 nodes. How do I measure the distance between these chords? Well, there are techniques to do this. So let's kind of put this on the side, and believe me when I tell you that we can still define a Euclidean metric in this generalized space. And the point is that here I have the elements of my network. The nodes are my chords, and the edges are defined by the distance between chords. Now, in this description, I'm actually considering every possible combination. So I'm not focusing on a specific set of chords, like a chord progression. No, I'm actually giving you a picture of the topology of all the possible combinations that you can build using these vectors as chords.
So you said I'll skip over it, but I'm quite curious what kind of space this is, because it's not a vector space.
No.
It's like a module.
Yes, and so the way in which you calculate distances is by adding, completing the lower dimension vector with duplicates of the same pitch, and then finding what is the combination that gives you the minimum distance.
Funny, okay. Does it have a name, this kind of object?
Does it have a name? Well, it's bijective, non-bijective distances.
Okay.
In vector space.
Yeah, I was just wondering, so in this first example you have this O 2,2,0.
Yeah.
So what would be so you say that you use Euclidean, so does it mean that
then you calculate just the square.
It's the square root of
the square root of the number squared.
Yeah. So does that make
well,
sense?
I mean, if you, it makes sense because you can see that this distance is equivalent to what in music theory is called voice leading. That means the closest path that your fingers would follow on the keyboard to go from one chord to another. That's the complete idea of voice leading, and it's kind of foundational in classical counterpoint and harmony. So this is actually an example of a voice leading distance. So, to specialize, this is an example of one of such networks. This is actually more for picture than for anything, because this is a network of I think 4 node chords in a 24 equal temperate space, so it's way larger than the one for triads. Yes?
So the set of nodes in this network is fixed, right? Because you don't consider like adjacent possible, like new nodes that can arrive to the system.
No, in this case, these are all the chords you see here, all these little points are all 4 node chords. So there is no dynamics now. The dynamics will come later. But let's kind of specialize more. Let's suppose we want to look at the triadic harmony, so the chords with 3 notes, that is the foundation of classical harmony, and classify and look at the topology of the network that emerged from links, so no connection at a particular distance. That means that in this network here, each chord connects to the next chord where only one note is changed by one semitone. So C, E, G becomes C, E flat, G. And it gives you, this particular shape. There are connections. You can look at this connection in terms of chord progressions, how you go from one particular chord region to another particular chord region and so on. Then you can change it. You say, okay, now I want to change two semitones instead of one. So I go from a triad like C, E, G to C, D, G. So I change one note by two. Or I change two notes by one, because that would be the same distance. And you see that at that point, the triads the two networks are separated. There is no connection between the family of chords and another family of chords. You can do the same for all the distances you want. So this is square root of 3, and you see that there is kind of a nice toroidal topology for the majority of chords, and this little island here. What happens is that these are the augmented triads that are separated from the others. So you kind of see how now there are objects that change position depending on the distance that you are looking at. Yeah.
If you mean triad, do you mean what musicians know to be triad?
Yeah.
Do you mean
Three-note chord.
Yeah, but I think that the musician would probably think that the triad is something like what you say, the C, E, G kind of thing. Yeah.
These are triads in a chromatic space, so there is not diatonic triads. It's all possible triads.
Okay. Yeah.
So we live in a
I should probably think of triplets. Triplet has another meaning in music as well.
No, triplet is a rhythmic figure. So yeah. I mean, there is rhythm also. Yeah. Rhythm of the networks, but it becomes way more complicated. Yes.
What are the colors?
Can you see on the left, for example, this is somehow also like one common way to introduce one half step down is like going from major to minor.
Yeah.
Is that something you can see in
Yeah,
there?
here.
Obviously.
Here you basically you can follow paths in this network where you are changing from major to minor.
Yeah, can you see that clearly? What the major ones are and the minor ones are, or?
Well, now I can't read here because but we can look at the images better on the computer. These are all they are numbered using the Forte classification. So these are in modern music theory we talk about pitch class sets as a generalized way of looking at vertical sonorities, and these are the classification from from this kind of approach. But of course, this is it's kind of a picture of well, this is another example, more complicated, but you have here how you build this voice leading distance from different chords. I mean, this is it's another paper that it's a little bit more complex from a musical point of view, but it's still part. I mean, it's one of the ways you can use this classification in a predictive way. Okay, but these are synthetic networks. We are building them by putting all this data together. There is no. Oh yeah, sorry.
Sorry for interrupting you, but in the previous picture, did you also compute the clustering coefficient and compare with the random geometric graph having the same distance to see whether
these are not. I mean, this one. The interest in this particular work is because in the 70s there was a kind of influential paper by some music theorists and composers that we're looking at this particular form of 12-tone roll that is the kind of the foundational element in atonal music and serialism. These are tone rolls that contain all the possible intervals in the roll, and they were interested in seeing what is the relationship between one of these rolls with other rolls, and what this study showed is that, you can actually find a relationship and isolate different classes of these all tone rolls or interval rolls that can be useful from a computational compositional perspective. It's kind of, this is very niche, so I wouldn't focus too much on this one. But yeah, yes.
Sorry. On the shape that you had earlier on the network, were there some nodes that are external and some that are internal, or it's just because the way
because of the topology, how the topology
so
works.
they have different degrees.
Yes, so they have different degrees, and there are some that cannot be connected by that distance.
And that's
So these are all. In this picture, everything, all the nodes have the same distance from the neighbors. So each neighbor has the same distance as the next neighbor. And if you do that, there are some cases where the network is separated. Okay, so but composers don't do like this. Composers, choose a particular progression. They build ideas on top of this progression. So it's in a way the composer is what is the agent that induces a probabilistic model in this network. So what do I choose here? What do I choose on the other side? Looking at this from this perspective gives a way of, on one hand, finding ways of new interpretations or analysis, and on the other one, tools for composing. Now, I want to give you an example. This is the network built on the harmonic structure of this chorale by Bach, and we can actually listen to it, and you'll see what happens. So this is the evolution of the piece as seen on a network. Now there are various things that we can observe in this example. The first one is clearly we have movements that are not symmetric, and the links here are directional, and the thickness of the link means how many times the link is visited in the composition. And the other thing is that I didn't choose the color of these nodes. The color of these nodes is determined by the modularity index, so one of these community structure measures on the topology of the network itself. And it's clear from listening to looking how the piece navigates through the network that each color corresponds to a different key. So there is a different tonal center in each of the colors. That means that the topology of the network tells us already something about the harmonic structure of the piece. So, yes?
Just to see if I understand what the edges are.
Edges, here I'll show you.
So I thought it's how often this movement is.
Yeah.
So how is it possible that in this top loop, for example, not all edges are equally thick? Because you can only traverse the full loop. Right? So D, F sharp, A sharp to B, D, F, G is very thin. But then the next step is much thicker.
We should look at the movie again. Now you asked me a difficult question. I don't know. But it doesn't matter.
Okay.
At this
It
point.
has something to do with how often you do that.
Yeah.
Okay.
It's basically how often it goes from one to the other.
Okay.
So there are some, for instance, they have clearly a more directional link because it's a 5-1 progression. There is
Right.
more from 5 to 1 than from 1 to 5.
Sure.
And all these things. Okay. But how can we actually quantify this in a way that is more kind of analytical and how and actually how do we get to this kind of representation? So change composer, but now I can show you how I build these networks. Take the string quartet from Beethoven on the late string quartet, and basically what I'm doing here is I'm slicing the score with a different with a particular quantization in rhythm, and I take each of these slices as one instance of a chord. So the first slice is a E flat major, the second slice is another E flat major, the third slice is a B flat 7, and so on. So this is the way in which I build these notes. And then every time I have a transition from one chord to the next, I have a link. And so this is how I'm counting what's happening in the score. So I call this the score network. Now, the score network is characterized by 4 properties of networks that are centricity, referentiality, directedness, and hierarchy. Clearly, you can see centricity from the degree distribution of the nodes. There are nodes that are way more in diameter, they are larger because they have more links connecting to them. So they are connected with more than others. There are modularity classes, the different colors that come from, again, the analysis of the topology of this network. The network is directional and asymmetric. There are clearly different loops or directions that the network takes. And there is a distribution between modularity classes and degree. So you have some modularity classes for which the degrees are smaller and others for which the degrees are larger. Well, you can look at this as if you put this on a graph, you see that basically we're looking at a scale-free network. This is the typical behavior of a scale-free network that represents this musical space. Well, but these 4 properties of a scale-free network are also properties of tonal harmony. So tonal harmony is governed by a few central chords. There is a hierarchical structure between these chords. There is a preference for asymmetric chord progressions, as we were saying earlier, 5 to 1, more than 1 to 5. And this hierarchical structure is clear at every level of the composition, not just on the kind of structural part, but also on the compositional part of this network. So, in a way, what I'm suggesting here is that what we are seeing by analyzing the network is the emergence of the model that the composer used in this particular case is the tonal harmony of the 18th century. So, common classical harmony. Well, we can look at the score also in another way, because right now I showed you this network as a temporal representation. Everything is at the same time on this network, and I just move around the link on the links in the process. But I can look at this same construction as a time series, where I add one chord, where each time stamp, time set is a quantization of the score, and I add every time there is a new chord, I add the point. This is a new chord here, so that 0 is always E flat major, 1 is always B flat 7, and C minor is 2, and so on. So every time there is another E flat major, I have a point that appears on this the x-axis, for instance. This is a time series. A time series that I can analyze in various ways. I can use common segmentation algorithms for score time series. This is using this this package in Python that does the analysis using different metrics. But I can also use more network-based concepts, like the concept of visibility network for time series that I know you're familiar with. Basically, it's a geometrical construct that builds a network out of the points in your time series. And we can analyze what happens in each of these regions as segmented by these algorithms. So, this is if I take, say, this segmentation and I build a network for each of these regions. So this is the first network that I build, that's the second network that is connected to the previous one, and so on. You get something like this. So each segment is a particular network. And if you go and look at what happens in these particular segments, you see that, again, you are isolating regions of different tonal centers, different keys. So here, for instance, we are, I believe we are in E flat major, the central chord here, and these are all the chords that belong to the E flat major key. And then I have a modulation where the next tonal center is a G minor. And you see that the G minor here was a very, relatively small node in terms of degree, and now becomes a more important node in the next layer. And you keep doing this, and you see how you can isolate the different sections. And this is kind of interesting because it allows you to do automated analysis. Because even if you know what is the key of a piece, you can computationally basically analyze the piece and say, oh, this chord is this chord, this particular dominant, this is the subdominant, blah, blah, blah. And you can write an analysis based on this kind of procedure. So here we have the segmentation algorithm, here we have the visibility network, and if you look one-to-one, you see that basically they both give us the same kind of analytical representation of the piece. Yes?
So, of course, it's kind of music. From this time, it's very much, chopped up into pieces, exposition, and then all the parts don't really need to for. So, how many elements of the piece are we looking at here? Is it just exposition or already?
No, this is the whole first movement.
So can you then, you have all these sections, do they overlap with what a music theory?
Yeah, it overlaps. I mean, you can see it from here. So this is what a music theorist would do. Like, this is the first section is in E flat major, then you have G minor, then you have C minor, and all these parts correspond to a particular section of the quartet. And so you can say, okay, this one is exposition, degrees, whatever. And so in fact, the piece actually goes back to E flat. I mean, it's another form is actually here. It's in this data.
But you have, depending on the algorithm, you get two different sections. But
no, they are not. I mean, you have to go, if you go in the different ranges, there are some, the algorithm sometimes kind of divides the same section in two, but it's the same section because they are still the same chord in the same key. And the same happens here too. I mean, these three, so from 385 to 490, it's all in flat major. And so it kind of makes sense. Some of them are, so for instance, here you have only 7 chords that are missed here, but it's with an A flat major that comes, well, some A flat something that comes at that point. Okay, so this is all nice, but can I use it in kind of a generative environment? How can I address this problem if I want to start from something that is not existing? Well, you can start by looking at this at the problem of what if I have a network that I want to navigate, and I want to navigate in the minimum number of steps, but still go through all the chords. So this is a route optimization problem on a directed network, and it seems, I mean, from the analysis of the backgrounds that are very minimalist in this respect, they are parsimonious in this way. The solution that the algorithm of a route optimization problem gives is very close to what actually Bach does. So the optimal solution will be 110 steps, and it does in 117.
We're speed running by.
Bach was speed running already.
But from here, what you can do is, we've seen already that at least in the classical harmony of the 18th century, and this is actually, it is true for most of Western classical music, but not only, scale-free networks are the topology, the general topology of music networks. So what we can do, we can build a scale-free network, like for instance, a Parabasi-Albert preferential attachment network, or any other kind of model that gives you something that is similar to this. Yes?
How would you describe the scale-free property in musical terms?
Yeah, I mean, in this case, it's more kind of the consequence of the structure, because you don't actually go and see at different scales that is the same geometry, right? Because you have only these chords. But I think that the interesting property here has to do with the perception of the music, because we are actually perceiving the structure ourselves when we listen to it, in terms of repetitions, in terms of the specific chords you end up with. So it has to do with either innate or culturally assigned perception of the music in these terms. Yes.
And what you mentioned about the VA and wisdom,
Yeah.
the pencil touch and to generate scale-free. But you know, this is randomization process. So every time I run the algorithm, I end up with different network.
So this is
how can I make sure that the node, the hub is that
no,
network?
but because here there is a big difference. You know, composers, they don't want to reproduce anything. They want to create something that is new.
Yeah, but
so in this case, let me tell you how I do this. Yeah. And then you listen to it. But so this is randomly generated. With the so what I do, I take the chords from the Bach chorale with their probability distribution, and I assign these chords to nodes of this network according to the same probability distribution. So that higher degree nodes in Bach, they are also higher degree nodes in this network. So the distribution follows one or the other, but the geometry here is completely different. Then you run the Postman algorithm, and basically you generate this new score network, and then on top of that, you take the chords and you compose. So this is an example of the original Bach and what comes out of this procedure that I just told you, where I put the notes on the stuff. I mean, this is not completely automated, but very similar. This is artificially generated, basically. I mean, I put some, I recomposed it, but I mean, the core progression is what comes out of that network. And basically, this process is become somewhat central to my way of composing. I'm not interested in composing another background, but I use this concept. I've used it in various pieces that you can find on my website. You can look at the scores.
So this is sort of indicated in Bach. There's this very strict counterpoint thing going on.
Yeah.
And this appears to be lacking in the recomposed version.
Yeah.
All the fancy.
Yeah, of course, because you are navigating on a random network.
Yeah, so this means that some sort of this counterpoint structure is not represented in your network. This communication between different voices,
because the way in which Bach was composing was the result of a training that was very strict on very specific contrapuntal structures.
Yes.
So basically, he was in a way limited in the phase space because he was looking only at the different progressions that he was taught. And he came up with different progressions, but we're all in the same kind of tradition, right? Here, it's completely open. So in a way, you could, with the argument of looking at Beethoven, I get the emergent property, I get tonal harmony as an emergent property. Here you could get a different kind of tonal harmony as an emergent property. But I'm not interested in these kind of things. I mean, for me, it's more, I'm looking at this as another tool that I can use as a composer to write something that is not influenced by my knowledge. And that's something very central for many composers. Right? You don't want to write music as somebody else, you want to write music as you, and this is a way of finding new perspective, new avenues of doing that. Okay, at last, I want to give you a few thoughts on universality of complexity, more from a point of view of like statistical mechanics, or talking about entropy and informations. So basically, out of these representations in terms of complex networks, we can extract measures of complexity in different ways. We look at three different ways of measuring complexity in network topology. One based on looking at the Kullback-Leibler divergence of the conditional degree matrix. So again, it's a measure of how one distribution differs from a reference distribution. And we can do this on a corpus, or we can look at different corpora, so that we can look also at within the same composer, for instance, how the distribution changes in terms of this quantity. We look at another measure, this diffusion entropy analysis, that is a time series method that compares basically, in very simple terms, you are looking at how your sequence relates to a random walk. And so you measure the entropy out of that. And then we use a completely different measure that is not even based on the network of chords that I've been talking about for the whole last hour. But kind of it's this computable information density is a data compression tool, and you look at data compression as a quantification of order. The more ordered is the sequence, the more you can compress it, and so on. So this is a result. This is with diffusion entropy analysis. So we look at different composer in different periods. This is chronologically ordered, and you see that if you believe me that this is a number that can somewhat measures the complexity of the harmonic structures, you see that the complexity raises, going from Renaissance polyphony to kind of more modern harmonic structures, in Mahler, for instance, or Brahms.
What is each point?
So each point is it's a composition, and I'm giving you the average and the standard deviation here.
How do you choose which compositions to
Oh, these are all the compositions that are available in the digital form that I will found.
Okay.
So this is a corpora. These are corpora. It's a corpus of a composition in music XML format.
Yeah.
So in principle, this is it's a graph that can be augmented if you have more data.
Because I assume that 20th century is not public enough yet. I mean, it would be interesting to have 12 tones here.
I'll show you. I'll show you not with this data. I'll show you with another kind of data. But so that's a comparison with some more popular music or more recent popular music, and not surprisingly, Franz Zappa was one of the most complex ones. This is the same data, but now with the Kurbach-Leiber divergence. So instead of having something that goes up, as we will see in diffusion entropy, we see something that goes down with complexity. So this is completely consistent with the other analysis we did for the same authors. Now,
Is the Kurbach divergence between what and what?
sorry?
Is the Kurbach divergence between what and what?
Yeah, one is this diffusion entropy analysis with the you use the relation between the time series with the random walk. In the other case, you use the conditional degree matrix to calculate this term as an entropy. But I mean, you expect this one to go down in complexity and this one to go up in complexity. So we are seeing the same result. Basically.
Why would this? So you're getting more close to a general reference as time progresses. Getting closer to the reference distribution.
Well, close to the average.
Yeah.
We are using the average over the whole corpora in this case.
And why does that mean more complex if you're getting closer to the average?
We can talk about it. I need to think about it. Okay, but so these are I mean, these two examples. But what we also did, and this is kind of interesting, we used the Spotify API. That it doesn't give you, of course, the waveform, the wave file itself of the piece of music that you're listening to, but it gives you quantitative measures that you can use for analysis, and this is what they use for doing for training the algorithms that give you the suggestions for next song and so on. And one thing that they have is the chroma vector, that is in a way very similar in concept to my dynamical score network, because each point here gives the probability distribution of the different pitches at that time. So it's kind of a picture of the chords in the score.
And there's 13.
Yeah, you see that you have this, the log power spectrum gives you the, and then they are reduced to the 12 tone. So basically you have, this is a, I don't know, whatever is probably C sharp or G, B, something. They knows with that probability. Now, what we can do with this is to look at this. Look at this quantity. That is this computable information density, where we use basically a comparison between the compressed, the size of the compressed versus uncompressed file. So this is a ASCII file. One is the compressed one is the original, and we look at this ratio that gives an information about the complexity. And we see the same kind of behavior we were seeing in the Kurbach-Leibler divergence. So what is very interesting here is that in this analysis we use a lot of time of data, because we use 5,000 tracks per composer. Of course, there are a lot of repetitions because the same piece has been recorded by many people. But I mean, this is all there. But the interesting aspect is to look at on this side. You have Schoenberg before 1913 and Schoenberg post 1913, and you see how when he adopted the atonal serial process in music composition, there is a big difference in the complexity of what he was writing. So I think that it was very interesting to see this in quantified in this way.
Are any of the other composers, do they have a similar pattern where if you split it in a year?
I didn't try.
Okay.
So, but that now up is more complex, right?
No, the up here is less complex.
Less
actually,
complex.
because it's more random.
Right.
So it's closer to a random walk than before. Before it was more structured, and now it's less structured. That is something actually that you can see also when you do the analysis of many of these pieces from a computational perspective. So when I teach a course on music coding where we do a computational model of some of these more modern pieces, and you see how computationally this kind of get closer to a random model than a structured one.
So this means that in this sense, complex is the opposite from what we intuitively
Yes.
talk about in classical music.
Yes.
Okay.
In fact, this is a big contentious problem when you talk with. You have to explain what complex means, and I always say complex doesn't mean complicated. And one has to be very careful because what we mean by complex in a statistical mechanics kind of complexity science sense is different from what. I mean, it's related, of course, but not exactly the same intuitively thing that you would. Yes.
But complexity in terms of compressibility can be a combination of both, right? Because you sometimes
It can be
much more
combination.
random.
Yeah, it can be combination of both.
Because here you're measuring the compression. Right?
Here I'm measuring compression. Yeah, yeah. Okay, so I developed over the years a large library of Python tools for doing all these things. These are all open source with examples. You can install it through pip, but you have also examples on my GitHub. You find links to all this in my websites, and there are papers so that you can look at. They're always linked. They're also linked in my website. So let's go back to the beginning with an epilogue. And if you remember, a few years ago, there was this news. There were these news all over the place, like mysterious radio signals from stars. And so the question is, what if this was music?
Thanks, Marco. Questions were already in between, so well.
I have just a very small question regarding about what you say that the musicians, they want to be more creative, they don't want to repeat other, right? So is it true that if I understand you correctly, you can design some objective function like depending on the audience taste of music, and then you can optimize the network, creating.
Yeah, in principle, yes. So you can the Mozart loss function.
Because so far it
then
seems like
you build networks distribution, of course, as if Mozart was writing a piece of music. I mean, this is all possible. I mean, it's not very efficient at this point. All these commercial AI generative systems are very efficient in reproducing music of other people, but they are not particularly creative.
But would this work? I mean, if you're talking about the audience, it wouldn't just be Mozart, it would be different tastes in the audience. But
Yeah.
then if you combine those, maybe what comes out is appealing to no one.
Maybe.
Because then you're
Yeah.
combining and then these
Yeah.
ratios don't hook up anymore.
Yes, very possible. But this is not how they do it.
I had a question. So, if you do this random walk to generate this new composition,
Actually, it's not a random walk.
sorry, the minimum walk,
Yeah.
the shortest
Okay.
walk over the random ground.
Yeah.
Do you have you found any things, any statistical properties that are not preserved compared to the
I
original?
don't know. No, I didn't look for it.
Okay. Because I wonder, because you said the counterpoint
It was also
is somehow not captured by the
And
optimal
also-
one.
the new graph was much less structured than the original graph. But it
Yeah.
looks like the topology was much more random
Yeah.
than.
Yeah.
So there is something in the topology that you're.
Yeah, I mean, these are open questions.
Yeah.
I didn't look into those.
And of course, these cantatas, they have at least two voices that interact. And of course, I think your analysis only focused on one voice.
No, my analysis focuses on the combination of the four.
So all the voices
All the
together
four, yeah,
are
from
stretched together
chords.
into one chord.
Yes.
No, they form the chord.
They form.
The
Yeah,
four
but-
voices.
Yeah, what I mean is that in counterpoint you get.
Yeah, there is no counterpuntal structure.
No, yeah,
This is all based on
because-
harmony.
Yeah, it's just
Yeah.
these different voices have to move in different.
Yeah,
directions.
different ways.
Yeah.
Yes.
Yeah,
Yeah.
but that
But you
could
can
be
build that in, right?
captured by exactly this network structure, right? Because that's exactly the movement is captured.
Because
by
the movement is dictated by voice leading.
No, but you,
Yeah, but
And so the voice leading is actually dictated by the topology, but the way in which one voice goes into the other is your choice.
yeah, you can choose to
You can choose how you do it.
to include that in the voicing.
So in the example of the artificial chorale that was the one built on the random network, I chose how to move the
Sure,
voices
yeah.
because there is no assignment of a particular. So I get the chords, but I don't get like the ordering of the pitches.
Yeah.
So I can assign pitches to any different voice.
Did you play the chords in the, because you did this graph for the map pieces, and then you looked at the optimal path, and there is like slightly shorter, right? It's,
Yeah.
did you try to play just to see how if the harmony and the way the progression is, does it still sounds very much like the Bach, or there is some places where maybe the ordering is slightly different?
I mean, you can hear from the example that there is a different ordering. I mean, it
And in
sounds
the example, you
different.
use a different graph, right? And then in the first case,
Oh,
you
you
use the
mean
graph,
on
and
the
then you-
same?
yeah, on the same graph,
It's basically the same.
It's basically the same.
It's basically the same.
I think so. There were you also only
Yeah.
lost
And
about
actually,
7 chords.
this is common to if you look at the 377 chorales and you plot the difference between. I have a graph somewhere. It's basically all published.
Okay, so the topology is extremely structured.
Yeah,
Because
it's extremely structured.
Because I think in the Barabasi network graph, you can find many almost optimal graph, almost
Yeah.
optimal path.
Yeah, yeah,
Because in the other
This-
one, there is
yeah.
one.
yeah. Yeah, I mean, in principle, there's a lot of work to be done, but I'm 1%. And I prefer going to music festivals than physics conferences.
This is one more global
Yeah.
question. And it's like, where do you want this procedure to go? I mean, in some senses, I can tell you that there is structure in music because that's just how we've been taught music. So in what sense do you think or hope to add with this program on top of whatever is written down in the classic textbook or music harmony?
No, first of all, you forget the classic textbooks.
Yeah.
Out. And then you build something yourself. But I think that the important connection here, I mentioned it in the talk, is our perception. So we perceive music in a kind of a topological space where there are firm points. I mean, if you analyze, for instance, the structure of melodies across the globe, there was a study a few years ago where they looked at different kind of songs and the structure of the different kind of songs. If you look at those structures and you analyze it with these tools, I'm sure that you find the same kind of behavior where you have higher degree notes that are the firm points where you land at the end, and you have all the passing notes.
I'm not sure if that's, I mean, so that work that you showed for Bach, this is just really very much because...
No, but you can see it everywhere. And you can, I mean, in you know, pop music, it's
for pop music is Western music, but if you would go to, you know, typical Indonesian gamelan music, something like that, I would be really surprised if the structure of the network would be the same to Western.
I mean,
music.
I didn't do an analysis of the gamelans. It's a little complicated to do it in terms of harmony because it's a very different structure, completely different way of looking at things. But if you look at more intimately human songs, you find the same topology. You know,
But this
nursing songs, wedding songs, funeral songs, in across cultures, and you see a very similar structure. And so, my point is that I can build topologically the same structure, but I populate with things that are completely alien to what is our innate, our cultural predisposition when we listen to music.
Do you then imply that this, because it's not just the structure, right? I mean, clearly there's a difference between just having the structure and then having the music that comes from that structure, as we heard from the two examples. But are you implying that all you need is the structure and then it's just culture that determines what structure you end up
No,
with? Because I think
it's not. I mean, it's at a certain point it becomes way more. I mean, you can't isolate one thing from the other. It comes all together. It comes with the performance. It comes with the expectation of that music in a particular context. Again, it's a complex adaptive system in that sense, in multiple scales.
Yeah, but I think there's something fundamental about certain aspects. I mean, certain things come back, even outside of Western music. Certain elements from.
They come back, even if you analyze bird songs or whale songs.
Yeah.
It has to do with some evolutionary biological thing.